Hello everyone, welcome to my audiobook. Today's lesson is from Ncert Chemistry Part 1, Class 11, Unit 5, Thermodynamics. So let's start now. It is the only physical theory of universal content concerning which I am convinced that within the framework of the applicability of its basic concepts, it will never be overthrown, said by Albert Einstein. Chemical energy stored by molecules can be released as heat during chemical reactions when a fuel like methane, cooking gas, or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated, and under certain conditions, these may be transformed from one form into another. The study of these energy transformations forms the subject matter of thermodynamics. The laws of thermodynamics deal with energy changes of macroscopic systems involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and at what rate these energy transformations are carried out, but is based on initial and final states of a system undergoing the change. Laws of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some of the important questions through thermodynamics, like how do we determine the energy changes involved in the chemical reaction or process? Will it occur or not? What drives a chemical reaction or process? To what extent do the chemical reactions proceed? Thermodynamic terms. We are interested in chemical reactions and the energy changes accompanying them. For this, we need to know certain thermodynamic terms. These are discussed below. First one, the system and the surroundings. A system in thermodynamics refers to that part of universe in which observations are made and remaining universe constitutes the surroundings. The surroundings include everything other than the system. System and the surroundings together constitute the universe. The universe equals to the system plus the surroundings. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings are that portion of the remaining universe which can interact with the system. Usually, the region of space in the neighborhood of the system constitutes its surroundings. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reaction mixture is the system and the room where the beaker is kept is the surroundings. Note that the system may be defined by physical boundaries like beaker or test tube, or the system may simply be defined by a set of Cartesian coordinates specifying a particular volume in space. It is necessary to think of a system as separated from the surroundings by some sort of wall which may be real or imaginary. The wall that separates the system from the surroundings is called boundary. This is designed to allow us to control and keep track of all movements of matter and energy in or out of the system. Types of the system. We further classify the systems according to the movements of matter and energy in or out of the system. First one, open system. In an open system, there is exchange of energy and matter between system and surroundings. The presence of reactants in an open beaker is an example of an open system. Here, the boundary is an imaginary surface enclosing the beaker and reactants. Second one, closed system. In a closed system, there is no exchange of matter, but exchange of energy is possible between system and the surroundings. The presence of reactants in a closed vessel made of conducting material, example copper or steel, is an example of a closed system. So these are the pictures you can see. Figure 5.2. You can pause it and you can check it. Next, third one, isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surroundings. The presence of reactants in a thermos flask or any other closely insulated vessel is an example of an isolated system. Next, the state of the system. The system must be described in order to make any useful calculations by specifying quantitatively each of the properties such as its pressure P, volume V and temperature T, as well as the composition of the system. We need to describe the system by specifying it before and after the change. You would recall from your physics course that the state of a system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of the state of a system is introduced. It does not need detailed knowledge of motion of each particle because we deal with average measurable properties of the system. We specify the state of the system by state functions or state variables. The state of a thermodynamic system is described by its measurable or macroscopic bulk properties. We can describe the state of a gas by quoting its pressure P, volume, temperature, amount, N, etc. Variables like P, V, T are called state variables or state functions because their values depend only on the state of the system and not on how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends on the nature of the system. Once these minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surroundings can never be completely specified. Fortunately, it is not necessary to do so. Next, the internal energy as a state function. When we talk about our chemical system losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical or any other type of energy you may think of. The sum of all these is the energy of the system. In thermodynamics, we call it the internal energy, U of the system, which may change when, first one, heat passes into or out of the system. Second, work is done on or by the system. Third, matter enters or leaves the system. These systems are classified accordingly as you have already studied in section 5.1.2. First one, work. Let us first examine a change in internal energy by doing work. We take a system containing some quantity of water in a thermos flask or in an insulated beaker. This would not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and surroundings. Here, the wall separating the system and the surroundings is called adiabatic wall, figure 5.3. Here 5.3 figure is given, an adiabatic system which does not permit the transfer of heat through its boundary. Okay, all these pictures I will be providing at the end of this audiobook. You can check it out. Let us bring the change in the internal energy of the system by doing some work on it. Let us call the initial state of the system as state A and its temperature as TA. Let the internal energy of the system in state A be called UA. We can change the state of the system in two different ways. One way, we do some mechanical work, say 1 kilojoule, by rotating a set of small paddles and thereby churning water. Let the new state be called B state and its temperature as TB. It is found that TB greater than TA and the change in temperature delta T equals to TB minus TA. Let the internal energy of the system in state B be UB and the change in internal energy delta U equals to UB minus UA. Next, second way. We now do an equal amount electrical work with the help of an immersion rod and note down the temperature change. We find that the change in temperature is same as in the earlier case, say Tb minus Ta. In fact, the experiments in the above manner were done by J.P. Joule between 1840 to 50, and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produced the same change of state as measured by the change in the temperature of the system. So, it seems appropriate to define a quantity, the internal energy U, whose value is characteristic of the state of the system, whereby the adiabatic work WAD required to bring about a change of the state is equal to the difference between the value of U in one state and that in another state, delta U. That is, delta U equals to U2 minus U1 equals to adiabatic work, that is WAD. Therefore, internal energy U of the system is a state function. By conventions of IUPAC in chemical thermodynamics, the positive sign expresses that WAD is positive when work is done on the system and the internal energy of system increases. Similarly, if the work is done by the system, WAD will be negative because internal energy of the system decreases. Can you name some other familiar state functions? Some of other familiar state functions are V, P and T. For example, if we bring a change in temperature of the system from 25 degrees centigrade to 35 degrees centigrade, the change in temperature is 35 degrees centigrade minus 25 degrees centigrade equals to plus 10 degrees centigrade. Whether we go straight up to 35 degrees centigrade or we cool the system for a few degrees, then take the system to the final temperature. Thus, T is a state function and the change in temperature is independent the route taken. Volume of water in a pond, for example, is a state function because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tube well or by both. Next, second one is heat. We can also change the internal energy of the system by transfer of heat from the surroundings to the system or vice versa without expenditure or work. This exchange of energy, which is a result of temperature difference, is called heat, Q. Let us consider bringing about the same change in temperature, the same initial and final states as before, by transfer of heat through thermally conducting walls instead of adiabatic walls. Figure 5.4. This is the figure you can check. We take water at temperature TE in a container having thermally conducting walls, say made up of water and copper, and enclose it in a huge heat reservoir at temperature TB. The heat absorbed by the system water Q can be measured in terms of temperature difference TB minus TA. In this case, change in internal energy delta U equals to Q when no work is done at constant temperature, constant volume. By conventions of IUPAC in chemical thermodynamics, the Q is positive when heat is transferred from surroundings to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surroundings, resulting in decrease of the internal energy of the system. C. The general case. Let us consider the general case in which a change of state is brought about both by doing work and by transfer of heat. We write change in internal energy for this case as delta U equals to Q plus W. For a given change in state, Q and W can vary depending on how the change is carried out. However, Q plus W equals to delta U will depend only on initial and final state. It will be independent of the way the change is carried out. If there is no transfer of energy as heat or as work, isolated system, that is, if W equals to 0 and Q equals to 0, then delta U equals to 0. The equation 5.1, that is delta U equals to Q plus W, is mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy. That is, energy can neither be created nor be destroyed. Note: there is considerable difference between the character of the thermodynamic property energy and that of the mechanical property such as volume. We can specify an unambiguous absolute value for volume of the system in a particular state, but not the absolute value of the internal energy. However, we can measure only the changes in the internal energy, delta U of the system. Next, applications. Many chemical reactions involve the generations of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let us see how. 5.2.1 Work. First of all, let us concentrate on the nature of work a system can do. We will consider only mechanical work, that is pressure to volume work. For understanding pressure volume work, let us consider a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas is VI and the pressure of the gas inside is P. If external pressure is Px, which is greater than P, piston is moved inward till the pressure inside becomes equals to Pex. Let this change be achieved in a single step and the final volume be Vf. During this compression, suppose piston moves a distance L and its cross-sectional area of a piston is A. Then volume change equals to L into A equals to delta V equals to Vf minus Vi. We also know pressure equals to force by area. Therefore, force on the piston equals to Pex into A. If W is a work done on the system by movement of the piston, then W equals to force into distance. The negative sign of this expression is required to obtain conventional sign for W, which will be positive. It indicates that in case of compression, work is done on the system. Here, Vf minus Vi will be negative and negative multiplied by negative will be positive. Hence, the sign obtained for the work will be positive. If the pressure is not constant at every stage of compression but changes in number of finite steps, work done on the gas will be summed over all the steps and will be equal to epsilon P delta V. Figure 5.5b. This is the figure, you can check it out. If the pressure is not constant but changes during the process such that it is always infinitesimally greater than the pressure of the gas, then at each stage of compression the volume decreases by an infinitesimal amount dV. In such a case, we can calculate the work done on the gas by the relation, thus 5.3. We can check it out. Here, Pex at each stage is equal to P initial plus dP in case of compression. In an expansion process under similar conditions, the external pressure is always less than the pressure of the system. That is, Pex equals to P in minus dP. In general case, we can write Pex equal to Pin plus or minus dP. Such processes are called reversible processes. A process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surroundings are always in near equilibrium with each other. Processes other than reversible processes are known as irreversible processes. In chemistry, we face problems that can be solved if we relate the work done to the internal pressure of the system. We can relate work to internal pressure of the system under reversible conditions by writing equation 5.3 as follows. So this is the equation, you can check it out. Now the pressure of the gas PIN, which we can write as P now, can be expressed in terms of its volume through gas equation. For n mole of an ideal gas, that is PV equal to nRT. P equals to nRT by V. Therefore, at constant temperature, isothermal process, okay, this is the equation, you can check it out. Next, free expansion. Expansion of a gas in vacuum is called free expansion. No work is done during the free expansion of an ideal gas whether the process is reversible or irreversible. Now we can write equation 5.1 in number of ways depending on the type of processes. Let us substitute. Okay, this equation you can check it out. If a process is carried out at constant volume, delta V equals to 0, then delta U equals to QV. The subscript V in QV denotes that heat is supplied at constant volume. Next, isothermal and free expansion of an ideal gas. For isothermal, T constant, expansion of an ideal gas into vacuum W equals to 0 since PEX equals to 0. Also, Joule determined experimentally that Q equals to 0, therefore delta U equals to 0. Equation delta U equals to Q plus W can be expressed for isothermal irreversible and reversible changes as follows. First one, for isothermal irreversible change, Q equals to minus W equals to PEX of VF minus VI. Second one, for isothermal reversible change. So this is the equation, you can check it out. Just you can pause it and go through it. And for diabatic change also, Q equals to 0, delta U equals to WAD. Next, enthalpy H in that A useful new state function. We know that the heat absorbed at constant volume is equal to change in the internal energy, that is delta U equals to QV. But most of chemical reactions are carried out not at constant volume but in flask or test tubes under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write equation 5.1 as delta U equals to QP minus P delta V at constant pressure, where QP is heat absorbed by the system and minus P delta V represent expansion work done by the system. Let us represent the initial state by the subscript 1 and final state by 2. We can rewrite the above equation in this way. Okay, you can check it out, and this can be rearranged, and with this we'll get this equation 5.6. Now we can define another thermodynamic functions. The enthalpy H, Greek word enthalpion, to warm or heat content, as H equals to U plus PV. So equation 5.6 becomes QP equals to H2 minus H1 equals to delta H. Although Q is a path dependent function, H is a state function because it depends on U, P and V, all of which are state functions. Therefore, delta H is independent of path. Hence, QP is also independent of path. For finite changes at constant pressure, we can write equation 5.7 as delta H equals to delta U plus delta PV. Since P is constant, we can write delta H equals to delta U plus P delta V. It is important to note that when heat is absorbed by the system at constant pressure, we are actually measuring changes in the enthalpy. Remember, delta H equals to QP, heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions which evolved heat during the reaction, and delta H is positive for endothermic reactions which absorb heat from the surroundings. At constant volume, delta V equals to 0, delta U equals to QV. Therefore, equation 5.8 becomes delta H equals to delta U equals to QV. The difference between delta H and delta U is not usually significant for systems consisting of only solids and or liquids. Solids and liquids do not suffer any significant volume changes upon heating. The difference, however, becomes significant when gases are involved. Let us consider a reaction involving gases. If VA is the total volume of the gaseous reactants, VB is the total volume of the gaseous products, NA is the number of moles of gaseous reactants, and NB is the number of moles of gaseous products, all at constant pressure and temperature, then using the ideal gas law, we write, okay, so this is the total equation, you can check. P delta V equals to delta NGRT. This is equation 5.9. Hence, delta Ng refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. Substituting the value of P delta V from equation 5.9 in equation 5.8, we get delta H equals to delta U plus delta NGRT. So the equation 5.10 is equal for calculating delta H from delta U and vice versa. Next, B. Extensive and intensive properties. In thermodynamics, a distinction is made between extensive properties and intensive properties. An extensive property is a property whose value depends on the quantity or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. Those properties which do not depend on the quantity or size of matter present are known as intensive properties. For example, temperature, density, pressure, etc. are intensive properties. A molar property Xm is the value of an extensive property X of the system for 1 mole of the substance. If N is the amount of matter, Xm equals to X by N is independent of the amount of matter. Other examples are molar volume Vm and molar heat capacity Cm. Let us understand the distinction between extensive and intensive properties by considering a gas enclosed in a container of volume V and at a temperature T. Let us make a partition such that volume is halved, each part now has 1/2 the original volume V by 2, but the temperature will still remain the same, that is T. It is clear that volume is an extensive property and temperature is an intensive property. So these are the figures 5.6a, 5.6b. You can pause and check it out. Next, heat capacity. In this subsection, let us see how to measure heat transfer to a system. This heat appears as a rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transferred. The magnitude of the coefficient depends on the size, the composition and nature of the system. We can also write it as Q is equal to C delta T. The coefficient C is called the heat capacity. Thus, we can measure the heat supplied by monitoring the temperature rise, provided we know the heat capacity. When C is large, a given amount of heat results in only a small temperature rise. Water has a large heat capacity, that is, a lot of energy is needed to raise its temperature. C is directly proportional to amount of substance. The molar heat capacity of a substance Cm equals to C by N is the heat capacity of 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. For finding out the heat Q required to raise the temperatures of a sample, we multiply the specific heat of the substance C by the mass M and temperature changes delta T as Q equals to C into M into delta T equals to C delta T. Next, the relationship between Cp, Cv for an ideal gas. At constant volume, the heat capacity C is denoted by Cv, and at constant pressure, this is denoted by Cp. Let us find the relationship between the two. We can write the equation for heat Q at constant volume as Qv equals to Cv delta T equals to delta U. At constant pressure as Qp equals to Cp delta T equals to delta H. The difference between Cp and Cv can be derived for an ideal gas as for a mole of an ideal gas. So this is the one, you can check it out. Okay. So overall 5.12 equation and 5.13 equation you can check. Next, measurement of delta U and delta H, calorimetry. We can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine the heat evolved in the process by measuring temperature changes. Measurements are made under two different conditions. First one, at constant volume QV, second one at constant pressure QP. Next is delta U measurements. For chemical reactions, heat absorbed at constant volume is measured in a bomb calorimeter, figure 5.7. These figures I will be providing at the end of this audiobook, you can check it out. Here, a steel vessel, the bomb, is immersed in a water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surroundings. So this is the figure. Okay. A combustible substance is burnt in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change. That is, the energy changes associated with reactions are measured at constant volume. Under these conditions, no work is done as a reaction is carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as delta V equals to 0. Temperature change of the calorimeter produced by the completed reaction is then converted to QV by using the known heat capacity of the calorimeter with the help of equation 5.11. Next is delta H measurements. Measurement of heat change at constant pressure, generally under atmospheric pressure, can be done in a calorimeter shown in figure 5.8. We know that delta H equals to QP at constant P, and therefore heat absorbed or evolved QP at constant pressure is also called the heat of reaction or enthalpy of reaction. In an exothermic reaction, heat is evolved and system loses heat to the surroundings. Therefore, QP will be negative and delta RH will also be negative. Similarly, in an endothermic reaction, heat is absorbed, QP is positive and delta RH will be positive. So in figure 5.8, calorimeter of measuring heat changes at constant pressure, atmospheric pressure has been given. You can please check it. Next is enthalpy change, delta RH of a reaction, reaction enthalpy. A reaction enthalpy. In a chemical reaction, reactants are converted into products and are represented by reactants gives rise to products. The enthalpy change accompanying a reaction is called the reaction enthalpy. The enthalpy change of a chemical reaction is given by the symbol delta RH. Okay, so this figure you can check it out, 5.14 figure you can check. Here symbol sigma is used for summation and AI and BI are the stoichiometric coefficients of the products and reactants respectively in the balanced chemical equation. For example, for the equation CH4 plus 2O2 gives CO2 plus 2H2O, where HM is the molar enthalpy. Enthalpy change is a very useful quantity. Knowledge of this quantity is required when one needs to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. Next, standard enthalpy of reactions. Enthalpy of a reaction depends on the conditions under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. Standard state of solid iron at 500 Kelvin is pure iron at 1 bar. Usually data are taken at 298 Kelvin. Standard conditions are denoted by adding the superscript, the symbol, to the symbol delta H. Next, enthalpy changes during phase transformations. Phase transformations also involve energy changes. Ice, for example, requires the heat for melting. Normally, this melting takes place at constant pressure, atmospheric pressure, and during phase change. Temperature remains constant at 273 Kelvin. H2O gives rise to H2O, liquid, that is solid, gives rise to liquid, equals to 6 kilojoules per mole. Here, delta fusion H is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surroundings. The enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Melting of a solid is endothermic, so all enthalpies of fusion are positive. So here they have given table 5.1 standard enthalpy changes of fusion and vaporization. We can pause it and check it. Water requires a heat for evaporation. At constant temperature of its boiling point Tb and at constant pressure H2O liquid gives rise to H2O gaseous, which it forms plus 40.79 kilojoules per mole. That means it will absorb. Okay, and is this delta vapor H is the standard enthalpy of vaporization. Amount of heat required to vaporize 1 mole of a liquid at constant temperature and under standard pressure 1 bar is called its standard enthalpy of vaporization or molar enthalpy of vaporization. Sublimation is direct conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 195 Kelvin with delta sublime H equals to 25.2 kilojoules per mole. Naphthalene sublimes slowly, and for this it is 73 kilojoules per mole. Standard enthalpy of sublimation is the change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature and under standard pressure 1 bar. The magnitude of the enthalpy change depends on the strength of the intermolecular interactions in the substance undergoing the phase transformations. For example, the strong hydrogen bonds between water molecules hold them tightly in liquid phase. For an organic liquid such as acetone, the intermolecular dipole-dipole interactions are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. Table 5.1 gives the values of standard enthalpy changes of fusion and vaporization for some substances. Next is table 5.2 they have given. Please, you can check it. Next, standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states of aggregation, also known as reference states, is called standard molar enthalpy of formation. Its symbol is delta FH. where the subscript F indicates that 1 mole of the compound in question has been formed in its standard state from its element in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen is H2 gas and those of dioxygen, carbon and sulfur are O2 gas. See graphite and S rhombic respectively. Some reactions with standard molar enthalpies of formation are as follows. So this is the one, you can check it out, and overall delta FH is it gives minus 277.7 kilojoules per mole. It is important to understand that a standard molar enthalpy of formation delta FH is just a special case of delta RH, where 1 mole of a compound is formed from its constituent elements as in the above 3 equations, where 1 mole of each water, methane and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction equals to minus 178.3 kilojoules per mole is not an enthalpy of formation of calcium carbonate, since calcium carbonate has been formed from other compounds and not from its constituent elements. Also, for the reaction given below, enthalpy change is not standard enthalpy of formation. Delta RH equals to minus 178.3 kilojoules per mole. Here 2 moles instead of 1 mole of the product is formed from the elements, that is delta RH equals to 2 delta FH. Therefore, by dividing all coefficients in the balanced equation by 2, expression for enthalpy of formation of HBr is written as, so this is the one, and delta FH equals to minus 36.4 kilojoules per mole. Standard enthalpies of formation of some common substances are given in table 5.2. By convention, standard enthalpy for formation delta FH of an element in reference state, that is its most stable state of aggregation, is taken as 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide with all the substances in their standard state. Here we can make use of standard enthalpy of formation and calculate the enthalpy change for the reaction. The following general equation can be used for the enthalpy change calculation. So this is the equation you can check, 5.15, where A and B represents the coefficients of the products and reactants in the balanced equation. Let us apply the above equation for decomposition of calcium carbonate. Here coefficients A and B are 1 each. Therefore, overall it gives rise to 178.3 kilojoules per mole. Thus, the decomposition of calcium carbonate is an endothermic process and you have to heat it for getting the desired products. Next, thermochemical equations. A balanced chemical equation together with the value of its delta RH is called a thermochemical equation. We specify the physical state along with allotropic state of the substance in an equation. For example, the equation it overall gives minus 1367 kilojoules per mole. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. It would be necessary to remember the following conventions regarding thermochemical equations. First one, the coefficients in a balanced thermochemical equation refers to the number of moles, never molecules, of reactants and products involved in the reaction. Second one, the numerical value of delta RH refers to the number of moles of substances specified by an equation. Standard enthalpy change will have units as kilojoules per mole. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction. Fe2O3 plus 3H2 gives 2Fe plus 3H2O. From the table 5.2 of standard enthalpy of formation, we find delta FH equals to 0 as per convention. Then delta FH1 equals to minus 33.3 kilojoules per mole. You can check the calculations. Here you can just pause and check the calculations. Next, note that the coefficients used in these calculations are pure numbers which are equal to the respective stoichiometric coefficients. The unit for delta RH is kilojoules per mole, which means per mole of reaction. Once we balance the chemical equation in a particular way as above, this defines a mole of reaction. If we had balanced the equation differently, for example, this is the equation, then this amount of reaction would be 1 mole of reaction and delta RH would be, so this is the calculation. It shows that enthalpy is an extensive quantity. Next, third point. When a chemical equation is reversed, the value of delta RH is reversed in sign. For example, so this is the equation, you can check it. Okay, next. Hess law of constant heat summation. We know that enthalpy is a state function. Therefore, the change in enthalpy is independent of the path between initial state reactants and final state products. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. This may be stated as follows in the form of Hess law. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Let us understand the importance of this law with the help of an example. Consider the enthalpy change for the reaction C graphite S plus half O2 gives rise to CO. Delta RH equals to how much? Although CO, which is in gaseous form, is a major product, some CO2 gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, if we can find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. Let us consider the following reactions. So these are the reactions, two reactions. Please check it out. We can combine the above two reactions in such a way so as to obtain the desired reaction. To get 1 mole of CO on the right, we reverse equation 2. In this, heat is absorbed instead of being released. So we change sign of delta RH value. Adding equation 193, we get the desired equation for which delta RH equals to minus 110.5 kilojoules per mole. In general, if enthalpy of an overall reaction A to B along one route is delta RH and delta RH1, delta RH2 and it's so on, representing enthalpies of reactions leading to same product B along another route, then we have delta RH equals to delta RH1 plus delta RH2 plus delta RH3 and goes on. It can be represented as, okay, this is the one, you can check it out. Next, enthalpies for different types of reactions. It is convenient to give name to enthalpy specifying the types of reactions. This first one, A, standard enthalpy of combustion. Combustion reactions are exothermic in nature. These are important in industry, rocketry, and other walks of life. Standard enthalpy of combustion is defined as the enthalpy change per mole or per unit amount of a substance when it undergoes combustion and all the reactants and products being in their standard states at the specified temperature. Cooking gas in cylinders contain mostly butane, C4H10. During complete combustion of 1 mole of butane, 2658 kilojoules of heat is released. We can write the thermochemical reactions for this as, so this is the thermochemical reaction, you can check it out. Similarly, combustion of glucose gives out 2802 kilojoules per mole of heat, for which the overall equation is, so this is the equation. Our body also generates energy from food by the same overall process as combustion, although the final products are produced after a series of complex biochemical reactions involving enzymes. Next, enthalpy of atomization. So here they have given the symbols for each one, you can check it. Consider the following example of atomization of dihydrogen. H2 gives rise to 2H. Delta AH equals to 435 kilojoules per mole. You can see that H atoms are formed by breaking H to H bonds in dihydrogen. The enthalpy change in this process is known as enthalpy of atomization. Delta AH, it is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecules like dihydrogen, the enthalpy of atomization is also the bond dissociation enthalpy. The other examples of enthalpy of atomization can be CH4 gives rise to C plus 4H. Here the delta AH equals to 1665 kilojoules per mole. Note that the products are only atoms of C and H in gaseous phase. Now see the following reaction. So this is the reaction. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. Next, C, bond enthalpy. This is the symbol delta bond H. Chemical reactions involve the breaking and making of chemical bonds. Energy is required to break a bond and energy is released when a bond is formed. It is possible to relate heat of reaction to changes in energy associated with breaking and making of chemical bonds. With reference to the enthalpy changes associated with chemical bonds, two different terms are used in thermodynamics. First one, bond dissociation enthalpy. Second one, mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecules. First one, diatomic molecules. Consider the following process in which the bonds in 1 mole of dihydrogen gas H2 are broken. H2 gives 2H, delta H to H bond H equals to 435 kilojoules per mole. The enthalpy change involved in this process is the bond dissociation enthalpy of H to H bond. The bond dissociation enthalpy is a change in enthalpy when 1 mole of covalent bonds of gaseous covalent compound is broken to form products in the gas phase. Note that it is the same as the enthalpy of atomization of dihydrogen. This is true for all diatomic molecules. For example, these are the two examples they have given. Just please pause it and check it out. I am not reading all these reactions because if you see, then you can easily catch it. Okay, if I read also, you may not clearly catch each and every point in it. In the case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. Next is polyatomic molecules. Let us now consider a polyatomic molecule like methane CH4. The overall thermochemical equations for its atomization reaction is given below. So this is the reaction. In methane, all the 4 CH bonds are identical in bond length and energy. However, the energies required to break the individual CH bonds in each successive step differ. Okay, so these are the steps you can see. You can please pause it and check it. We find that mean CH bond enthalpy in methane is 416 kilojoules per mole. It has been found that mean C to H bond enthalpy differs slightly from compound to compound, as in CH3, CH2, Cl, CH3NO2, etc. But it does not differ in great deal. Using Hess law, bond enthalpies can be calculated. Bond enthalpy values of some single and multiple bonds are given in table 5.3. This table also I will show you. Okay, at the end of the audiobook also you can check it. The reaction enthalpies are very important quantities as these arise from the changes that accompany the breaking of old bonds and formation of the new bonds. We can predict enthalpy of a reaction in gas phase if we know different bond enthalpies. The standard enthalpy of reaction delta RH is related to bond enthalpies of the reactants and products in gas phase reaction as. So this is the 5.17 equation. This relationship is particularly more useful when the required values of delta FH are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Remember that this relationship is approximate and is valid when all substances, reactants and products in the reaction are in gaseous state. So here they have given table 5.3a, some mean single bond enthalpies in kilojoules per mole at 298 Kelvin. Okay, you can check it. And next 5.3b, some mean multiple bond enthalpies in kilojoules per mole at 298 Kelvin. Okay, please check these two. Next, lattice enthalpy. The lattice enthalpy of an ionic compound is an enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. Since it is impossible to determine lattice enthalpy directly by experiment, we use an indirect method where we construct an enthalpy diagram called as Born-Haber cycle, figure 5.9. Let us now calculate the lattice enthalpy of Na plus Cl minus by following steps given below. First one, Na solid gives rise to Na gaseous. Sublimation of sodium matter. Delta sublimation equals to 108.4 kilojoules per mole. So here they have given figure 5.9 enthalpy diagram for lattice enthalpy of NaCl. Please check it. Next, second point. Na in gaseous state gives rise to Na plus gaseous state plus 1 electron. The ionization of sodium atoms ionization enthalpy delta IH equals to 496 kilojoules per mole. Next, third one. 1 by 2 Cl2 gaseous form gives rise to Cl gaseous form. The dissociation of chlorine. The reaction enthalpy is half the bond dissociation enthalpy. Next, fourth point. Cl in gaseous form plus 1 electron in gaseous form gives Cl minus gaseous. Electron gained by chlorine atoms. The electron gain enthalpy delta EGH equals to minus 348.6 kilojoules per mole. You have learnt about ionization enthalpy and electron gain enthalpy in unit 3. In fact, these terms have been taken from thermodynamics. Earlier terms ionization energy and electron affinity were in practice in place of the above terms. See the box for justification. Okay, these green boxes also I will be providing at the end. Next, fifth point. Na plus in gaseous state plus Cl minus in gaseous state gives rise to Na plus Cl minus in solid. The sequence of steps is shown in figure 5.9 and is known as Born-Haber cycle. The importance of the cycle is that the sum of the enthalpy changes around a cycle is 0. Applying Hess law, we get, this is the equation. Internal energy is smaller by 2 RT because delta Ng equals to 2 and is equal to plus 783 kilojoules per mole. Now we use the value of lattice enthalpy to calculate enthalpy of solution from the expression. So here is the expression, please check it. The dissolution of NaCl in solid form is accompanied by very little heat change. Next, enthalpy of solution, symbol delta solution H. Enthalpy of solution of substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interactions between the ions or solute molecules are negligible. When an ionic compound dissolves in a solvent, the ions leave their ordered positions on the crystal lattice. These are now more free in solution. But solvation of these ions, hydration in case solvent is water, also occurs at the same time. This is shown diagrammatically for an ionic compound ABS. Okay, this is the figure, you can check it. The enthalpy of solution of ABS delta solution H in water is therefore determined by the selective values of the lattice enthalpy and enthalpy of hydration of ions. For most of the ionic compounds, delta solution H is positive and the dissolution process is endothermic. Therefore, the solubility of most salts in water increases with the rise of temperature. If the lattice enthalpy is very high, the dissolution of the compound may not take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitudes of enthalpy changes may be made by using tables of bond energies, enthalpies, and lattice energies, enthalpies. Next is enthalpy of dilution. It is known that enthalpy of solution is the enthalpy change associated with the addition of a specified amount of solute to the specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen chloride in 10 moles of water can be represented by the following equation. For convenience, we will use the symbol AQ for water, that is aqueous. HCl gaseous plus 10 aqueous gives rise to HCl into 10 aqueous. Delta H equals to minus 69.01 kilojoules per mole. Let us consider the following set of enthalpy changes. So these are the enthalpy changes. You can check it. The values of delta H show general dependence of the enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches a limiting value, that is the value of infinitely dilute solution. For hydrochloric acid, this value of delta H is given by in equation S3. So here S1, S2, S3 equations are given. You can check it. If we subtract the first equation, equation S1 from the second equation, in the above set of equations, we obtain HCl 0.25 aqueous plus 15 AQ gives HCl 0.40 aqueous. Overall, you can check it all the equations, set of equations, and what we obtain. Overall, we get minus 0.76 kilojoules per mole. This one will get, this value will get. This value minus 0.76 kilojoules per mole of delta H is enthalpy of dilution. It is the heat withdrawn from the surroundings when additional solvent is added to the solution. The enthalpy of dilution of a solution is dependent on the original concentration of the solution and the amount of solvent added. Next is spontaneity. The first law of thermodynamics tells us about the relationship between the heat observed and the work performed on or by a system. It puts no restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon in dioxygen giving carbon dioxide. But heat will not flow from colder body to warmer body on its own. The gas in a container will not spontaneously contract into one corner, or carbon dioxide will not form carbon and dioxygen spontaneously. These and many other spontaneously occurring changes show unidirectional change. We may ask, what is the driving force of spontaneously occurring changes? What determines the direction of a spontaneous change? In this section, we shall establish some criterion for these processes, whether these will take place or not. Let us first understand what do we mean by spontaneous reaction or change. You may think by your common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactants. Take the case of combination of hydrogen and oxygen. These gases may be mixed at room temperature and left for many years without observing any perceptible change. Although the reaction is taking place between them, it is at an extremely slow rate. It is still called spontaneous reaction. So spontaneity means having the potential to proceed without the assistance of external agency. However, it does not tell about the rate of the reaction or process. Another aspect of spontaneous reaction or process, as we see, is that these cannot reverse their direction on their own. We may summarize it as follows. A spontaneous process is an irreversible process and may only be reversed by some external agency. A. Is decrease in enthalpy a criterion for spontaneity? If we examine the phenomenon like flow of water downhill or fall of a stone onto the ground, we find that there is a net decrease in potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because decrease in energy has taken place, as in the case of exothermic reactions. For example, these are the reactions. Please check it. The decrease in enthalpy in passing from reactants to products may be shown for any exothermic reaction on an enthalpy diagram as shown in figure 5.10a. Thus, the postulate that driving force for a chemical reaction may be due to decrease in energy sounds reasonable as the basis of evidence so far. Now, let us examine the following reactions. So, please check these reactions. Now, the figure 5.10a, enthalpy diagram for exothermic reactions. These reactions, though endothermic, are spontaneous. The increase in enthalpy may be represented on an enthalpy diagram as shown in figure 5.10b. This is the figure. Therefore, it became obvious that while decrease in enthalpy may be contributory factor for spontaneity, but it is not true for all cases. Next, second one, entropy and spontaneity. Then what drives the spontaneous process in a given direction? Let us examine such a case in which delta H equals to 0. That is, there is no change in enthalpy, but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container which is isolated from the surroundings as shown in figure 5.11. The two gases say gas A and gas B are represented by black dots and white dots respectively. So these are the figures respectively and separated by a movable partition. When the partition is withdrawn, the gases begin to diffuse into each other and after a period of time diffusion will be complete. Let us examine the process. Before partition, if we were to pick up the gas molecules from left container, we would be sure that these will be molecules of gas A, and similarly, if we were to pick up the gas molecules from right container, we would be sure that these will be molecules of gas B. But if we were to pick up molecules from container when partition is removed, we are not sure whether the molecules picked are of gas A or gas B. We say that the system has become less predictable or more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for a system's energy to become more disordered or chaotic, and this could be a criterion for spontaneous change. At this point, we introduce another thermodynamic function, entropy, denoted as S. The above mentioned disorder is the manifestation of entropy. To form a mental picture, one can think of entropy as a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. As far as a chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactants to another in the products. If the structure of the products is very much disordered than that of the reactants, there will be a resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated qualitatively by consideration of the structures of the species taking part in the reaction. Decrease of regularity in structure would mean increase in entropy. For a given substance, the crystalline solid state is a state of lowest entropy, most ordered. The gaseous state is state of highest entropy. Now let us try to qualify entropy. One way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method, which is beyond the scope of this treatment. Other way would be to relate this process to the heat involved in a process, which would make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal energy U and enthalpy H, is a state function, and delta S is independent of path. Whenever heat is added to the system, it increases molecular motions, causing increased randomness in the system. Thus, heat Q has randomizing influence on the system. Can we then equate delta S with Q? Wait, experience suggests us that the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it. than one at lower temperature. Thus, temperature is a measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to it at higher temperature. This suggests that the entropy change is inversely proportional to the temperature. Delta S is related with Q and T for a reversible reaction as. So, this is the equation 5.18. The total entropy change for the system and surroundings of a spontaneous process is given by the equation 5.19. You can check it. When a system is in equilibrium, the entropy is maximum and the change in entropy delta S equals to 0. We can say that entropy for a spontaneous process increases till it reaches maximum, and at equilibrium the change in entropy is 0. Since entropy is a state property, we can calculate the change in entropy of a reversible process by this equation. You can see the equation here. We find that both for reversible and irreversible expansion for an ideal gas under isothermal conditions, delta U equals to 0. But delta S total, that is delta S plus delta S surroundings and systems, is not 0 for irreversible process. Thus, delta U does not discriminate between reversible and irreversible process, whereas delta S does. Next, Gibbs energy and spontaneity. We have seen that for a system, it is the total entropy change delta S total which decides the spontaneity of the process. But most of the chemical reactions fall into the category of either closed systems or open systems. Therefore, for most of the chemical reactions, there are changes in both enthalpy and entropy. It is clear from the discussion in previous sections that neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous change for these systems. For this purpose, we define a new thermodynamic function, the Gibbs energy or Gibbs function G, as G equals to H minus Ts. Gibbs function G is an extensive property and a state function. The change in Gibbs energy for the system can be written as, so this is the one, you can check it please. At constant temperature delta T equals to 0, this is the equation. Usually the subscript system is dropped and we simply write this equation as delta G equals to delta H minus T delta S. This is equation 5.21. Thus, Gibbs energy change equals to enthalpy change minus temperature into entropy change and is referred to as Gibbs equation, one of the most important equations in chemistry. Here we have considered both terms together for spontaneity, energy and entropy, as indicated earlier. Dimensionally, if we analyze, we find the delta G has units of energy because both delta H and T delta S are energy terms. Since T delta S equals to overall it gives rise to J. Now let us consider how delta G is related to reaction spontaneity. We know, okay, delta S total equals to delta S system plus delta S surrounding. If the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in the enthalpy of the system. Therefore, entropy change of surroundings. So, this is the equation. Please check it out. You can pause it and check it. Because we cannot read all these reactions over here. Please pause and check it. Now, delta H system is the enthalpy change of a reaction. T delta S system is the energy which is not available to do useful work. So, delta G is the net energy available to do useful work and is thus a measure of the free energy. For this reason, it is also known as free energy of the reaction. Delta G gives a criteria for spontaneity at constant pressure and temperature. First point, if delta G is negative or less than 0, the process is spontaneous. Second point, if delta G is positive, the process is non-spontaneous. Note: if a reaction has a positive enthalpy change and positive entropy change, it can be spontaneous when T delta S is large enough to overweigh delta H. This can happen in two ways. First one, the positive entropy change of the system can be small, in which case T must be large. Second one, the positive entropy change of the system can be large, in which case T may be small. The former is one of the reasons why reactions are often carried out at high temperatures. Table 5.4 summarizes the effect of temperature or spontaneity of reactions. Next, entropy and second law of thermodynamics. We know that for an isolated system, the change in energy remains constant. Therefore, increase in entropy in such system is a natural direction of the spontaneous change. This, in fact, is the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In exothermic reactions, heat released by the reaction increases the disorder of the surroundings, and overall entropy change is positive, which makes the reaction spontaneous. Next, absolute entropy and third law of thermodynamics. Molecules of substance may move in a straight line in any direction. They may spin like a top, and the bonds in the molecules may stretch and compress. These motions of the molecules are called translational, rotational, and vibrational motion respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lowered, the entropy decreases. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. This is so because there is perfect order in a crystal at absolute zero. The statement is confined to pure crystalline solids because theoretical arguments and practical evidences have shown that entropy of solutions and supercooled liquids is not zero at 0 Kelvin. The importance of the third law lies in the fact that it permits the calculation of absolute values of entropy of pure substance from thermal alone. For a pure substance, this can be done by summing Q by T increments from 0 Kelvin to 298 Kelvin. Standard entropies can be used to calculate standard entropy changes by the Hess law type of calculation. Next is Gibbs energy change and equilibrium. We have seen how a knowledge of the sign and magnitude of the free energy change of a chemical reaction allows. First one, prediction of the spontaneity of the chemical reaction. Second one, prediction of the useful work that could be extracted from it. So far we have considered free energy changes in irreversible reactions. Let us now examine the free energy changes in reversible reactions. Reversible, under strict thermodynamic sense, is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up. This means that the reactions in both the directions should proceed with an increase in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So the criterion for equilibrium A plus B equals to, that is reversible reaction C plus D, is delta Rg equals to 0. Gives energy for a reaction in which all reactants and products are in standard state. Delta Rg is related to the equilibrium constant of the reaction as follows. So please check this reaction 5.23 and 5.24. For strongly endothermic reactions, the value of delta Rh may be large and positive. In such a case, value of K will be much smaller than 1 and the reaction is unlikely to form much product. In case of exothermic reactions, delta Rh is large and negative and delta Rg is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reactions to have a large K and hence can go to near completion. Delta Rg also depends upon delta Rs. If the changes in the entropy of reaction is also taken into account, the value of K or extent of chemical reaction will also be affected depending upon whether delta Rs is positive or negative using equation 5.24. Next, here they have given the table 5.4 effect of temperature on spontaneity of reactions. You can check it out. Next, it is possible to obtain an estimate of delta G from the measurement of delta H and delta S and then calculate K at any temperature for economic yields of the products. Second point, if K is measured directly in the laboratory, the value of delta G at any other temperature can be calculated using equation 5.24. Next is a summary of the lesson. Let's see. Thermodynamics deals with energy changes in chemical or physical processes and enables us to study these changes quantitatively and to make useful predictions. For these purposes, we divide the universe into the system and the surroundings. Chemical or physical processes lead to evolution or absorption of heat, part of which may be converted into work. These quantities are related to the first law of thermodynamics via delta U equals to Q plus W. Delta U, change in internal energy, depends on initial and final states only and is a state function, whereas Q and W depend on the path and not the state functions. We follow sign conventions of Q and W by giving the positive sign to these quantities when these are added to the system. We can measure the transfer of heat from one system to another, which causes the change in temperature. The magnitude of rise in temperature depends on the heat capacity C of the substance. Therefore, heat absorbed or evolved is Q equals to C delta T. Work can be measured by W equals to minus P delta V in case of expansion of gases. Under reversible process, we can put Px equals to P for infinitesimal changes in the volume, making W equals to minus P dV. In this condition, we can use gas equation PV equals to nRT. At constant volume, W equals to 0, then delta U equals to QV. Heat transfer at constant volume. But in study of chemical reactions, we usually have constant pressure. We define another state function, enthalpy. Enthalpy change delta H equals to delta U plus delta NGRT can be found directly from the heat changes at constant pressure, delta H equals to QP. There are varieties of enthalpy changes. Changes of phase such as melting, vaporization and sublimation usually occur at constant temperature and can be characterized by enthalpy changes which are always positive. Enthalpy of formation, combustion and other enthalpy changes can be calculated using Hess law. Enthalpy change for chemical reactions can be determined by this equation in gaseous state. In gaseous state, by delta RH equals to sigma bond enthalpies of the reactions minus sigma bond enthalpies of the products. First law of thermodynamics does not guide us about the direction of chemical reactions. That is, what is the driving force of chemical reaction. For isolated systems, delta U equals to 0. We define another state function, S, entropy, for this purpose. Entropy is a measure of disorder or randomness. For a spontaneous change, total entropy change is positive. Therefore, for an isolated system, delta U equals to 0. Delta S greater than 0. So entropy change distinguishes a spontaneous change while energy change does not. Entropy changes can be measured by the equation delta S equals to Q by T for a reversible process. Q reversible by T is independent of path. Chemical reactions are generally carried at constant pressure, so we define another state function, Gibbs energy, G, which is related to entropy and enthalpy changes of the system by the equation delta Rg equals to delta Rh minus T delta Rs. For a spontaneous change delta G system less than 0 and at equilibrium delta G system equals to 0. Standard Gibbs energy change is related to equilibrium constant by delta Rg equals to minus RT in K. K can be calculated from this equation. If we know delta Rg, which can be found from delta Rg equals to delta Rh minus T delta Rs. Temperature is an important factor in the equation. Many reactions which are non-spontaneous at low temperature are made spontaneous at high temperature for systems having positive entropy of reaction. Okay, so with this we are done with the lesson. If you like my audiobook, please share it to your friends, like and subscribe. If you have any comments, please post it in the comment box. I will answer you each and every question. Thank you.